So I have an idea for a way to create flight profiles for a launch without me needing to do all my trial and error. Run a simulation. Okay, that's a bit too low. Make this higher. Run it again. A bit too high. Make it low. Run it again. You know, this like constant iteration that I do manually at the moment. I'm trying to think of ways to automate that. So I have an idea in which here's an example of a mission. This is the Space IL lunar lander mission that SpaceX launched a few weeks ago. This is just stage 1 we're looking at. Go over to stage 2. Imagine I had a bunch, like maybe just like 5 or 10, like not too many points for, at this time altitude should be this, at this time altitude should be this, at this time altitude should be this, and so on and so on. And the same for velocity as well. So I have 5 or 10 points for altitude versus time and velocity versus time. And I say I want my trajectory to go through these points. I want it at these times, I wanted to have these altitudes and these velocities. And I'll need to make one guess. Well, I mean, the altitude and velocities will be guesses anyway, I suppose. But I will have to guess a throttle profile, which I don't think is that big a deal, because generally now SpaceX with their Block 5, they don't go to 100% throttle. They kind of stick around this 90, 96, 97, throttle down for max Q for a while, and then go back up again. ULA rockets like Atlas and Delta, they tend to just go 100%, go until there's no propellant left. Same with the solid rocket boosters, 100%, just until it's gone. Well, actually, Delta 4 medium SRVs had a throttle profile, but it was predetermined. It wasn't. There was no hocus pocus around it. It was like, before launch, this is what the throttle profile is going to be. It's the same for every launch, So I think that's okay to guess. So if I have a throttle profile, this kind of throttle curve here for the ascent until MECO, then I can figure out this thrust curve for the ascent until MECO. Because I know everything about the vehicle before the simulation. I know all the engine properties, like thrust and ISP for CO vacuum, all that stuff. I also know everything about the vehicle, like its dry mass and propellant mass, payload mass, fairing mass, all those different masses I know. So I know the vehicle mass at every point in time. So if I know the thrust at every point in time and the mass at every point in time, I can figure out the acceleration due to thrust. I also know the acceleration due to gravity because it's constant. Well, it depends on the mass, which I know. And that's always acting in the same direction, vertically down. I don't know the direction of the thrust vector because, at the start it's pointing straight up, and over time it curves over. And that's given by my elevation curve. So obviously it begins at 90 degrees, close enough to it. And then after 30 seconds, it starts to pitch over. It goes 60, 45, 30, and there MECO happens there around 27 degrees there. So the angle is like that angle there. That's the angle that I care about. So 90, 45, 30. So the vertical component of that is sine of that angle. So sine of 90 is 1, sine of 0 is 0. So if I know this angle at every point in time, then I know the vertical component of the thrust acceleration. So vertical thrust acceleration minus vertical gravity acceleration minus drag, which we don't know, but do you know what? Drag is kind of weak. We can just give it some constant value, right? We don't care that much. It's going to be good enough for approximation for now. With time, we can come back to drag. So let's ignore drag for now. Vertical thrust acceleration minus vertical gravity acceleration will give us our total vertical acceleration, which when we integrate with respect to time twice, will give us our altitude at every point in time. So we can try out different elevation curves, feed them into that integral, see what altitude figures come out, and we can iterate to minimize the difference between what we want and what we have. And the way I do that is something like a loss function, where you'd say you get the desired altitude values for every time you get what you have, you get the difference between them, and a common loss function is a root mean squared, where you'd get the squares of the differences, you'd add them all together, and then you would average. So you would square root. So you kind of get the average error over all your points. A bunch of different loss functions. I don't know what will be better in this case. I'm going to just go with root mean squared. I think that'll work, and then that would give me an elevation profile to match the altitude that I want. To match the velocities that I want, I could also, if I get the horizontal component of thrust, that's acceleration in the horizontal direction. Nothing else accelerates in the horizontal direction. And if I integrate that vertical acceleration once, that gives me the vertical acceleration, vertical velocity. Integrate that one once, give me the horizontal velocity. Square them, sum them, root them to get the magnitude. Would give me that. So I could also do a loss function on that. Would it give me anything extra? Not really. It might tell me if my throttle profile is bad, which I could feed back into that. Okay. I think that's a good start. That would get me as far as Miko. It wouldn't do anything for second stage. It wouldn't do anything for first stage returning. Boost back to entry burns, landing burns. I just need to know all the altitude versus time and velocity versus time points in my curve. And I think downrange will be inherently solved, because if I know my throttle curve and I know my acceleration, then I know how fast I'll be going. I know I'll be going seriously fucking fast at this point. So I wouldn't be able to just go straight up and have all the altitudes correct, because going that fast would send me up here. I'd need to turn over that way. So I guess I'd also need to set the launch azimuth to make sure it turns the right way. But I think it's doable. I think it's a good start. So I'm going to give it a go and see how we do.